Mhm. Well, are we at the main stage? We aren't yet.
We're in the main stage.
We are on the main stage?
Yep.
Okay. Well, everybody, thank you for coming to this wonderful, eventful April meeting of Orange County Astronomers. Everybody is welcome. Those of us that are here in the auditorium who are very patiently dealing with our sound issues here. And those of you who are in the remote audience, welcome all of you. And rather than me saying much, I think I will turn this over to the crew who is doing the announcements. So Kyle, you want to take that away?
Great. Let me just share screen. All right, here we go. Right. So we welcome all new members. If you're currently present at the meeting, your name badges will be present on the whiteboard in the next month or two. Otherwise, they'll be mailed to your home address. Star parties, just keep checking the online calendars. Those dates are still to be announced. Special interest group meetings. The astrophysics group is meeting April 21st at 7:30 at the Heritage Museum. The beginners class is meeting May 5th at 7:30 at the Heritage Museum. The board meeting is online at 11:30 a.m. on May 7th. You can check the website for information on all these events. Doug, do you want to speak about this at all? I'm assuming that's a yes.
Hi, this is Helen. Doug is not available at the moment, so I'll tell you about OVRO. This year, it's going to be June 23rd and 24th. And any of you who have been there before, we're going to have the kind of a wonderful program like we usually do. If you've never been, it's really fun. These are the big dishes that are on the way to, as you're driving 395 up to Bishop, that you see out on the right side. And we get a tour of the big one. We have a wonderful program talking about the science that's going to be done there, and the brand new facility that they're going to be building out in the Nevada desert. They're going to talk about that. That's going to be a huge radio astronomy with 2,000 telescopes. So you'll hear about that. We'll do liquid nitrogen stuff and then astronomy on Friday and Saturday night. So it's going to be a lot of fun. If you are interested at all, you can see, this is a little bit hard to see here, but you can contact Doug Millar, my husband, at DRZARKOF56 at yahoo.com. He's also on the back of the Serious Astronomer. He's one of the trustees, Doug Millar, and email him, let him know that you're interested in going, and he'll email you back with all the information. Okay.
Awesome. Keep going. Outreach events. Please join us in welcoming our new outreach coordinator, Jeff Gray. You can contact him at the email there below, outreach@ocastronomers.org. The coffee stand is open. You can get coffee, donuts, and water, $1 each, up at the library entrance for those who are in person. You probably saw it on your way in. Some good snacks. So if you're there, go up and see if anything looks tasty. The Adopt-a-Scope program is continuing. You can get more information about that online, and you can see there you can download an sample adoption agreement and download the current inventory. And there's more information on there about if you'd like to participate in the program, how to get involved with that and get a scope. Serious Astronomer newsletter. Dave Fisher is always looking for new content to put in the newsletter. So if there's any items that you think would be interesting, please email those items of interest to him at newsletter@ocaastronomers.org. Please remember that the newsletter is always available online to members. All members receive a mailed copy, but if you would like to opt out of receiving the paper copy, please let Charlie know. Again, everyone receives a printed copy mailed to their home address unless you opt out. Please remember to keep weeds clear at Anza. And then the next general meeting will be held May 12th. And I will turn it over to Chris Butler for the What's Up presentation. Thank you.
Okay, I guess I better jump in. Hi, everybody. Chris Butler here. Going to show you what's up in the sky for April here. Let's see. And all right, if we can see me, here we go, folks. What's going on in the sky this month? Well, first of all, here's your moon phase. We just had the last quarter moon in the morning sky when the moon was half lit. We're a couple days past that, so the moon is a waning crescent. So it's really going to be an early morning kind of thing coming around towards April 19th, which will be the dark of the moon. For casual observers who like to look at the moon in the evening sky, you're going to notice it reappearing around the 23rd, something like that, as a crescent in the evening sky. Full moon won't be until past the end of this month in the beginning of May. As far as the planets, Mercury and Venus are both very well placed in the west right now. Mercury is swinging out to an elongation, as we call it, where it's least obscured by the glow of the sunset. So it's a good time to look at it now, maybe another week, but I certainly wouldn't wait much longer than that. Venus, you've got a lot more time. Venus is going to be with us all through the next several months. It's 40 degrees from the sun in the evening in the west. It's very high, brightest thing in the sky except for the sun or the moon. If you can't find it, you can't be a member of the Orange County Astronomers. No, I'm just kidding. That's not true. But it is the brightest thing in the sky except the sun or the moon. So they've got that. Mars is still around. I'll show you where. It's in Gemini, the twins. It's not very bright, and it's certainly not very large in your telescope. We'll show you a diagram as to why that is. Jupiter is behind the sun right now. Obviously not a good time to look at Jupiter. Saturn is in the morning sky, pre-dawn, rises at 4:12 in the constellation of Aquarius. It's first magnitude. Yeah, you can see it. We'll show you where it is, but I'm not up that early, so I can't verify whether or not it's really there. I think it is. Uranus is actually in the evening sky. It's not far from where Mercury is right now, but unlike Mercury, Uranus is very faint and there's a lot of sky glow, so it's not a good time to look at Uranus. Neptune is very low in the dawn sky in the morning. It is not well placed. It's overwhelmed by the glow of dawn. Here's that diagram explaining why Mars is not good. You may remember in December we passed Mars. That's the center of this diagram. And Mars attained a larger angular size. It was much brighter in the sky and much better in your telescopes. But over on the right side of your slide, you see that's where we are now with Mars. Mars has shrunk to a very small size, and it is not even the brightest object to look at all in that part of the sky, not even in that constellation. So it really looks about like the other Gemini twin stars, Castor and Pollux. You'll see it on a chart in a second, but not a good time for Mars. When the sun first starts getting well below the horizon, 7:45 p.m., this chart here shows you Mercury lower in the west and Venus much, much higher in the west. So a good time to look for them. If you let the sky go ahead and darken the rest of the way, you can see Mars is there as well. Mars is down in the feet of Gemini, looking again about like Castor and Pollux as a first magnitude star, but not all that bright. Looking at stars in the sky, I want to make the point that Sirius, leading off the winter stars there, that train has moved off into the west, literally. It is setting in the west in the evening. Winter is most assuredly over. There are stars like Arcturus and Spica, which are rising in the east at this hour. And I'll draw your particular attention to Regulus. Regulus is almost, as you can see, straight overhead at 9 p.m. That means we're going to be having a look at Leo. Ah, yes, Leo, famous, beautiful, and very much not this Leo, by the way. Although I will point out that it's April 14th. Our meetings sometimes fall on this date, and it is the 111th anniversary of the sinking of the Titanic, which explains the situation with our AV tech. Leo the Lion as a constellation, though, is an ancient one. It is a bright one, an obvious one. It is one of the constellations in Ptolemy's star catalog, 48 constellations of antiquity. It is a constellation where sometimes planets, or indeed the sun and the moon, can pay a visit. Tonight, none of those are there. So it's just the stars of this wonderful pattern. As far as mythology, I've discovered a new thing that it's true with all constellations. This was the Nemean lion, and they have all these different things in mythology. But the basic idea is it's a creature, and Hercules killed it. Pretty much true with all the constellations, it seems like. Pick a favorite constellation. Hercules killed it. Do not invite Hercules to your parties, friends. He's just going to start slaying. It's what he does. Now, here's a modern astronomical chart of Leo from the International Astronomical Union. In blue, you see the path of the sun over the course of a year and where planets at times may be found. The pattern of Leo itself really does look like a lion. Yes, he's just lion there. It really does have a distinctive pattern. The bright star Regulus is one of the top 25 stars in the sky, a first magnitude star. For people who want to look a little deeper, you want to look at some objects, there are some there. Notice in red, we have some galaxies, distant galaxies beyond our own, labeled. And because Leo has a very obvious pattern, if any of you should have a telescope that doesn't have a computer that will automatically point you at everything, so why am I even saying this? But assuming you actually look for yourself, it's easy to find them in the pattern of Leo. There are two distinct groups. M96 and M105 are part of a whole group that's right under the middle of Leo. At the back part of Leo, M65 and M66 are some of my very, very favorite things to look at. And by the way, you can see them in the city with a decent-sized telescope. Here's a chart that I made a number of years ago showing some of the stars and also the stars next door of Cancer, the crab you see there. But notice the 2903, that's NGC 2903. That's a galaxy that is basically been blown out the nose of the snorting lion. And then the M95 group and the M65 group of galaxies located underneath. He's like sitting on them. Here's a wide field picture of M95 on your left and M96 on the right. They're both beautiful galaxies. M95 is a barred spiral galaxy, and you can see a little bit of a distortion in its shape. M96 even more so. Notice, by the way, in this beautiful ESO photograph, you see another galaxy there, kind of an orange-looking streak. That's not in M96. It's far beyond it. Just happens to be lined up that way. M95 and M96, by the way, are fairly nearby at a distance of about 30 to 35 million light years. That's freeway close as galaxies go. M105 is one of the neighbors there of that group. A perfectly featureless ball of light, an elliptical galaxy. Again, not a smudge on your lens. That is billions and billions of stars, a very large galaxy. In the other part of Leo, and these are my absolute favorites, M65 at top right, M66 there below it, and then the other side of the screen, NGC 6328. These are also part of that relatively nearby group of galaxies. galaxies, and therefore they're some of the brightest and most obvious galaxies in the sky. I will caution you that NGC 6328 is significantly fainter, and I have a tough time even spotting that from the city. M65 and M66, though, definitely easier. And there's the boogers blown out the nose of the lion, NGC 2903. This, of course, is a photograph taken by the Hubble Space Telescope, so it looks slightly better than what I see through my telescope. Hydra, I will also give you, and no, it's not these guys, not the bad guys from the Marvel Cinematic Universe that, quite frankly, I can't take very seriously. We're talking about this constellation. I've shifted over to midnight, and I want to let you guys know this is an all-night constellation this time of year. It is the longest constellation from east to west, and it is, in fact, the largest of all the constellations in the sky. I believe 1,300 square degrees of sky covered by this giant snaky-looking thing that is supposed to be a snake of some kind. Now, mythologically, this is the snake where you cut the head off and it grows another head or multiple heads or whatever. You know what happened to it? Can you guess what happened to it? Yep, Hercules killed it. Hercules killed it. Hercules kills everything. Notice along the path, though, there's a couple constellations that don't exist anymore. Some of them get dropped. And for some of you cat fans, looking at you over there, Suzanne, notice right below the snaky snake over on the right side of the screen, you have Felis, not Felix, Felis, the cat. Used to be a constellation. It is not anymore. And riding on the very tail, on the other side of the screen, far left, is Noctua, the night owl. That is not a constellation anymore. It's all part of Hydra. Here's a modern chart here where you can see this constellation laid out. It has a very distinctive looking pattern for a head. You can find that pretty easily in binoculars. The star Alphard is a second magnitude orange star, so it's pretty easy to see. Notice in particular, though, 3242, that's NGC to its friends, that is a planetary nebula in the middle part of the constellation. I'll show you a picture in a moment. M68 is just below the Crow, Corvus, and it is within Hydra. And then all the way at the other end, we've got M83 down at the bottom, almost in Centaurus, but it is technically a galaxy in Hydra. Here's NGC 3242, known as the Ghost of Jupiter, gas cloud blown off by a dying star. That's a very pretty, but again, this is an HST photograph. It won't look quite this good in your scope. This is a pretty realistic view for an amateur instrument of the globular star cluster M68. One of my favorites, and by the way, one that often gets overlooked every year. Don't forget it this time. It's in Hydra. And then the beautiful face-on spiral galaxy M83 in the tail of Hydra. Now, the nice thing about this is that this constellation is up for hours and hours and hours and hours as the sky rotates from left to right, from east to west in the seam. There's some part of Hydra that's up almost all night long. Now, if you do want to stay up later and let the dawn start to glow, you finally will see Saturn. I promise it's out there tonight. It's next to a waning crescent moon there. You'll see straight overhead the triangle of stars, Deneb, Vega, and Altair of the summer triangle at that hour. And we mentioned Neptune is out there, but you can see it's completely overwhelmed by the rising dawn. Well, gosh, that's a lot to keep you busy, folks. So with this beautiful close-up picture of M83 and Hydra, I hope you will spend some time with Leo and Hydra. And that concludes our What's Up presentation.
Thank you, Chris, for yet another great presentation. Wonderful. Hi, my name is Reza, and I'm the Vice President of the club. I, too, would like to welcome you to the general meeting of the Orange County Astronomers on April 14th, 2023. Our speaker at this meeting is a professor of astrophysics at the University of Arizona, specializing in building telescopes that go into space and the stratosphere, and developing technology to make telescopes better. She's a leader in the field of space astrophysics and has developed programs to teach early career scientists how to develop their own space missions. She is the Deputy Principal Investigator of Aspera, a NASA orbiting telescope in development. Please join me in welcoming Dr. Erica Hamden. Dr. Hamden.
Hello, can you guys hear me?
Yes, all clear.
Okay. So I'm like so happy to be here and talking to you, and I'm so impressed at how well organized your club is. And Chris, I love the presentation and all of the jokes. That was great. So I'm so happy to be here to talk to you guys about a little bit about the ultraviolet, which is the wavelength that I specialize in, and my own work. And hopefully there's enough interesting and beautiful pictures to keep you all entertained. Okay, so hopefully you're seeing my screen now.
Yes, all good.
Okay. So my talk is about observing the universe in the ultraviolet and challenging for astronomers on the ground. In order to observe in the ultraviolet, we have to go up into space or to the stratosphere. So this picture in the background, it was taken by a UV telescope called GALEX, which operated in the 2000s that took UV images of the sky. And this is actually a supernova remnant. And what you're seeing is molecular hydrogen that is fluorescing very gently, and that creates this like blue color in the GALEX images. So first, just to make sure that everyone comes along with me, I want to talk about like, what is the ultraviolet? So our eyes are specialized to see visible light. A lot of the astronomy that we do from the ground is focused on visible light, but of course there's lots of other wavelengths of light. And if we're interested in understanding how the universe works, we have to look at all wavelengths, not just the ones that are easily accessible. So the ultraviolet is a shorter wavelength than visible light. And it's a little bit more energetic. As you go into shorter and shorter wavelengths, like the X-rays, those are more energetic photons. The gamma rays are the most energetic photons. And then in the other direction from visible, you have infrared, which we sometimes think of as like thermal energy. And then microwaves, and then the least energetic, longest wavelength photons are the radio. So the ultraviolet is sort of along this continuum from the blue side of the visible wavelength, which is why it's called that, ultraviolet. It's like more violet than violet. And for stuff on Earth, we actually split it into these categories, UVA, UVB, and UVC, which you might know from your SPF. And it's fun. This is funny to me because as an ultraviolet astronomer, like I only care about UVC. UVA and UVB are like technically visible from the perspective of a UV astronomer. And for us, most of the light is blocked by the atmosphere, which is good for life on Earth. There's this like kind of bad joke in UV astronomy, which is that you could have UV astronomy from the ground or life on Earth, but you can't have both at the same time. So UV photons, when you're out, you know, in the summer, especially for me in Tucson, a lot of the UVA and UVB light is not blocked by the atmosphere. So we can just observe that from the ground. It penetrates at different levels into your skin, which is why it like can give you different degrees of sunburns. The UVC light and beyond in the what's called the vacuum UV, or we sometimes refer to it as the space UV, actually gets absorbed by the upper layers of the atmosphere. It's mostly the ozone layer, although it's also some just molecular oxygen that does the absorbing. And the sun doesn't really emit that much UV anyway. This is a plot of the solar spectrum, and the spectrum really peaks in the visible, which is why our eyes are adapted to see in the visible. And then it drops off pretty sharply into the UV and then into the X-rays. And this figure on the right, this is a log scale of the wavelength. So the ultraviolet range is kind of from 10 to the 2 to like, right, this like little blue line. So this blue line is the atmospheric cutoff where most of the far UV and what we would clarify as the near UV is blocked. And so the best place for UV observations is going to be above most of that atmosphere. This is sort of presenting some of the same information, but the UV rays that we're most concerned with are the ones that don't make it all the way down. Or there are some in kind of this in-between state that make it to the stratosphere, but not all the way down to the actual ground. So my work as a UV astronomer is focused on some of those UVB rays, and then even farther, more energetic into the UVC. And the atmospheric transmission is a big problem, not just for the ultraviolet, but for lots of other wavelengths. The X-rays, it's good for life on Earth that that X-ray photons don't make it to the ground, but it's not good for X-ray astronomy, so you have to put those telescopes in space. The same for gamma rays. And then actually, interestingly, in the infrared, parts of the infrared are visible from the ground, but then parts of it you have to actually be in space. Or there was a telescope on an airplane called Sophia, which was just recently retired. That was in sort of the like high altitude airplane areas. And then farther into longer wavelengths, we have a radio window where you can just put radio telescopes on the ground. So the atmosphere is transmissive at visible and then radio wavelengths. And just for some like, I don't know, general interest, I thought it'd be kind of cool to look at like what is actually causing this in the atmosphere. And it's it's a combination of many different things. So the middle gray plot is showing the atmospheric absorption. You can see it actually starts to ramp up in the visible wavelength, and then it really has a strong cutoff as you get into the UV. This is 300 nanometers. So this would be like the UV is starting somewhere around here. And that's mostly due to oxygen and ozone, although it's also due to some of the scattering that causes the sky to be blue. You're missing those blue photons because they're getting scattered around. Whereas the infrared absorption is actually water vapor in the atmosphere. And so that's part of why you can have some infrared telescopes, but they have to be at dry locations or like really high altitude. So all of this, the like sort of complicated atmosphere, which is great for us, is one of the reasons that drives my work to be focused on space and putting things above that atmosphere. And space telescopes are like a weird thing to work on. They're really cool, but they're also like very complicated and tricky. And I spent a little time thinking about like, why do we do this? Because it's really a lot of work. It's much easier to put your telescope on the ground. We didn't even really talk about the possibility of putting a telescope in space until this 1946 paper by a professor. At the time he was at Yale, who his name was Lyman Spitzer, and he wrote a paper called The Astronomical Advantages of an Extraterrestrial Observatory, where he basically wrote out the plan for the what became the Hubble Space Telescope. So this is from 1946. Of course, it took like 44 years until it actually got put up. And we all know the story of that telescope. But this idea, he like sort of talks about how there's all these advantages to having a space telescope and that we should figure out a way to put a telescope and point it. And he describes like a couple of different options, like a very small one that's only 10 inches, a bigger reflecting telescope that would be many feet in diameter, and like what you can do. And this was very prescient. The first telescopes that went up into space were launched actually in the 60s, and they were ultraviolet telescopes, again, because of this atmospheric blocking. Like you can have a visible wavelength telescope on the ground, but if you want to know what's happening with these other wavelengths, you have to put your telescope in space. So the wavelength advantage is one thing, but then there's actually a huge difference in what we as astronomers refer to as the seeing, just like the resolution that you can get with a telescope on the ground versus in space. And of course, like twinkling stars are really lovely, but if you're trying to take a picture of them, it's like very annoying. So this is showing the difference in the resolution from a telescope on the ground, the Subaru telescope, versus the Hubble Space Telescope for the same target. And so the top is sort of a wide field view, and then the bottom is a zoom in. And you can see so much more detail with the Hubble, even though it's a smaller telescope. It's 2.4 meters versus the Subaru 8 meters. And it's just because Hubble is above the atmosphere and doesn't have to deal with the twinkling, basically. So that's one big advantage. Of course, I would be remiss to not show this spectacular image, the JWST alignment image, which this was just to line up all of the mirrors in the telescope. And the point of this image is the like getting everything to focus on the star. But the best part about this image by far is like the background galaxies, because they're just so incredible and they're so sharp. And so this is like a JWST calibration image and the same part of the sky from the ground. This is an image from the DESI Legacy Imaging Survey. And like, you can't even tell that there are two galaxies here because the resolution is just not high enough. So having this like crystal clear view of the universe and at these wavelengths that you can't access in any other way is really, really important. So, so to go back to the UV, there's another motivation for it, which is that the night sky has really not been observed in the ultraviolet the way that other wave bands in the sky have been observed. So this is a little table showing different wavelength ranges. You have the visible, which has been observed. 100% of the sky has been observed in the visible. We've seen all of it many times over and taken images of it. In the infrared, near infrared, mid infrared, far infrared, we've looked at 100% of the sky. Interestingly, in the radio, we've only looked at about 77% of the sky. I don't know what's going on with that other 23%. And then if you go to the other side of the visible, gamma rays, X-rays, the extreme UV, we've seen 100%, but there's this section between the extreme UV and the visible where we haven't looked at big chunks of the sky. And this Lyman, this is Lyman UV, so it's from the Lyman continuum to about Lyman alpha. This is a really challenging wavelength range where this is not a typo, less than 0.03% of the sky has been observed. And then in the far UV and the near UV, what we would refer to as like the UVC, only 70% of the sky has been observed. And in that 70%, it's only the faint parts of the sky. So if you're curious of like, what does the Orion Nebula look like in the UV? We don't have an answer because we've never looked at it. And so there have been UV missions. The UV was actually, there was a UV telescope on Apollo 16 that the astronauts set up on the moon. The PI of that was this astronomer from Goddard named George Carruthers, who's actually kind of the father of UV astronomy. And he was an African-American astronomer who had a couple of missions in the 60s and 70s where he was like the only person, he's the single author of these papers. But there have been some really incredible discoveries in the UV when we do put telescopes in space, finding molecular hydrogen, which we think is one of the pieces of fuel for star formation, studying hot stars in the interstellar medium, measuring the universal deuterium amount. And so this image is actually of the Large Magellanic Cloud taken with the far ultraviolet camera spectrograph that was on the Apollo missions. And so as I've like learned more about the history of the UV and gotten interested in it from a scientific perspective, I've always been like, what is up with this? Why aren't there more UV telescopes? Why haven't we looked at every part of the sky in the UV? And there's a few reasons which I think kind of combine that make the UV a little bit harder than other wavelengths. The atmospheric transmission is challenging, but that's true for the X-ray. It's true for the infrared. The materials are very difficult, and this is a big thing. A lot of mirror surfaces or gratings or even the detectors themselves that work in the visible or they work in the X-ray don't work in the UV. You have to make these modifications to them. And that's because the UV photons are energetic enough to like damage your stuff, but not so energetic like X-rays that they'll just like punch through anything. And then the other reason is because there isn't really a military or commercial application for a lot of UV technology, because again, it's absorbed by the atmosphere. So like you can't use it on the ground. So I think these combine to just make things like a little bit harder than other wavelengths. So before I talk about my work, I wanted to talk a little bit about like what makes the universe in ultraviolet so cool and interesting. And the main thing is that the ultraviolet is a tracer of energy, like energetic events, bright stars, the deaths of stars in spectacular fashion, all sorts of like interesting processes, like radiative processes, are happening in the UV, and then frequently we observe them at some other wavelengths where you're seeing like a byproduct of the actual UV process. So one, of course, fantastic example is like, let's look at a nearby galaxy in different wavelength ranges. And so here I'm showing a radio image, infrared image, a visible wavelength image, ultraviolet image, and an X-ray image of Andromeda. And these are all the same field of view. And this is partly why it's important to take pictures of at different wavelengths, because each one is telling you something different about the galaxy or the star or the object. So in the infrared and the radio, we're looking at like dust and hydrogen. And you can see the beautiful like spiral structure really highlighted in those. In the visible, you're looking at a combination of dust and old stars and new stars. And it's like very jumbled up. It's a little harder to like pick out certain features. But then in the ultraviolet, you are looking only at new stars. So when star clusters are forming, you have a range of stellar masses. And the biggest, brightest stars will put out most of their photons in the UV, but then they die like pretty quickly. So if you have UV photons coming from star clusters, that means that the star cluster is, less than 100 million years old. And so you can tell where there's like new star formation happening in the galaxy. And that tells you kind of about like the environment of the galaxy. And then the X-ray is telling you about really energetic events, supernova or black hole activity. So the combination of all these wavelengths gives you a full picture of like the life cycle of the galaxy and what's happening. Another example is, of course, a little closer to home. So Jupiter, you can look at Jupiter in the UV and compare it to like visible wavelength lights and then infrared light. And this is like so cool because the infrared is almost the like opposite of what the UV is showing. And the visible is somewhere in between. So the infrared, like the great red spot, is actually very cold. So it doesn't show up as easily in the image. That's why it looks darker. But the UV light can be used to probe like different depths into the atmosphere. And so you can see different cloud heights than you would be able to see in the visible or with the infrared. And then the other thing that's interesting is like the poles of Jupiter are dim in the ultraviolet, again, because of like how the atmosphere is absorbing and reflecting back the UV photons. And then sticking with Jupiter, like if you look at it at the right time in the right place in the UV, it has these beautiful auroras, which actually is a little bit strange because the auroras on Earth are produced by the solar wind, but the auroras on Jupiter are actually from high energy electrons that come out of Io's atmosphere and then end up interacting with Jupiter's magnetic field at the poles. And you can watch these interactions in the ultraviolet. They don't really show up at other wavelengths. So you can see like not only Jupiter's magnetic activity, but you can also see how it's interacting with the stuff around it. And then if we go to the biggest object in our solar system, the sun is incredibly interesting in the ultraviolet, even though the peak is in the visible. As you move through different wavelength ranges in the ultraviolet, you're probing different layers of the sun's atmosphere and different kind of depths above the photosphere. And so you can see the activity at like 10,000 Kelvin. This is at 1600 angstroms. As you go now more into the extreme UV, you're seeing parts of the chromosphere, the upper transition layers, and then like actually where it joins with other parts of the corona that are much hotter, like 6 million Kelvin. And this picture I just threw in because I think it's like really amazing, but this was from 2012, a transit of Venus. So the black dot up here, this is Venus transiting across the sun. And then 3 different wavelengths, all in the ultraviolet combined. This is from the Solar Dynamics Observatory. And this dark area over here is actually a coronal hole where you're not getting that much emission in that section. But so you can see the like really active, beautiful magnetic field that's reflected in the UV photons, because that's where all the energy is happening, basically. And so I want to contrast that. I have these like, images of like, oh, here's Andromeda in the UV. There's tons of other galaxies in the UV. But if you're looking for like the brightest, most interesting objects in the sky in the UV, like this one, the Orion Nebula, like we don't have pictures of it in the UV because it's too bright. And one of the technology development projects that I work on is making detectors for the ultraviolet that are able to look at bright targets. And like, it feels nutty to be like, oh yeah, the brightest things, we like, don't look at them, because that's obviously the first things you should look at. But like, that's the reality for the UV, that the technology used in many of these missions has very limited dynamic range. And so if you look at bright stuff like the trapezium in the middle of the Orion Nebula, plus like you blow out the detector and then that's it. And I was looking at your website and I saw you guys had some pictures of Orion Nebula that somebody took, and like, they're not that different from these fantastic pictures. But so these pictures are visible in the infrared. And one thing I hope to do over my career is like provide another panel, which is like, what does the Orion Nebula look like in the ultraviolet? The 4 stars in the trapezium are 4 of the brightest stars in the ultraviolet, like in our galaxy, and we can't look at them. So there's lots of other parts of the UV that are like incredibly interesting and scientifically valuable. I actually clicked on this slide by accident, but there's regions around galaxies where you can look at different emission line tracers that are tracers of different densities and temperatures for like the halos of galaxies. Those all are emitted in the rest frame ultraviolet. If you're interested in exoplanets, the UV is critically important for exoplanets to know whether the planet can ever harbor life. So there's a lot of these small stars, M stars, that are smaller than the sun, and we're looking for planets around them because their habitable zones are kind of easier to detect planets in. But the flip side is that these stars can be like weirdly active. Our sun is relatively, ordinary. It's not doing too much, but the these M stars can have these huge flares where they send out a ton of UV and X-ray photons, and that's enough that they can irradiate the surface of the planet. So if you have a planet that could have an atmosphere or could harbor life, like the atmosphere is going to be changed significantly based on the UV activity of the star. So being able to observe those stars before we spend a bunch of resources trying to see if there's life on that planet, it'd be good to know, like, oh, well, the star radiates the planet every 100 years and there's no life on that planet. And the UV can tell you that. Another really interesting and kind of recent example is what we call multi-messenger astrophysics. So when you have a neutron star or black hole merger that gets detected with LIGO in gravitational waves, you want to do follow-up in the electromagnetic spectrum and see like what's happening with the photons in that region. And so this is a figure from the discovery paper for merging neutron stars. So two neutron stars that orbited around and then merged, and they explode as a supernova. And if you catch it at the right time, really early after the merger, there's actually a tremendous amount of UV photons and information in the UV spectrum. But so in this example, this is showing data from SWIFT, which is kind of a fast moving telescope that has a UV channel that got there in 1.2 days, but it's a very low resolution telescope, versus the Hubble Space Telescope, which by the time it got there in 5.5 days, like the UV part of the spectrum was over. This stuff cools off really quickly, which is why you see this over time, this line gets lower and the peak shifts to the red because it's cooling quickly. So we need UV telescopes that can do like rapid follow-up of these mergers and figure out how bright is the merger in the UV, what's the maximum temperature that's reached right at the beginning, and help us to understand like the processes that are happening right as the neutron star is exploding. So scientifically, there's lots of other things I like don't have time to tell you all about the wide world of UV astronomy, but there's other topics like galaxy evolution and composition, the large scale structure of the universe, the history of star formation, like within our own galaxy, studies of the interstellar medium of our own galaxy. So this wavelength range, there's like so much to do with it. And there's not enough UV telescopes to like do all of this work. So the other like interesting thing is that it's also easy to observe in. And I hope I'm not showing too many plots for you guys, but I feel like you're sophisticated astronomers. So this is from the Hubble Space Telescope Observing Handbook, and it's showing the contribution of different sort of night sky bright things. I'm like blanking on the word for it. The contribution from like Earthshine, zodiacal light, and geocoronal light at different wavelengths. And as you go into the ultraviolet, all of these drop off really significantly. So the right plot is a linear axis in flux, and then the left is the same thing, but with a log scale. And so as you go into the UV compared to the visible, which is over here, as you go into the UV, especially into the far UV, the zodiacal light from the solar system is like several orders of magnitude fainter than it is for visible wavelengths. So your night sky is super dark and you're able to observe really faint structures, really faint objects. So the UV has so much to offer and is like, actually, once you get your telescope into space, it's like pretty easy to observe in it. And the sort of landscape for UV astronomy has been kind of quiet for a long time. The only UV telescope that's like really operating in a serious way is the Hubble Space Telescope. SWIFT has a UV channel, but it's low resolution, and SWIFT is also at the sort of the end of its life. And so there's been a big push to get more UV telescopes up. And my own work, I started working on the ultraviolet when I was a graduate student. I was a graduate student at Columbia, but I worked with a group at JPL on developing ultraviolet detectors that were better than the previous state of the art. So this is a picture of one of the detectors. It's a silicon-based detector that's not that different from what's in your cell phone. We have a custom treatment that JPL does that makes the detectors UV sensitive. And so that work, so the previous state of the art, the detectors that cannot look at bright objects, the Galax NUV and Galax FUV, near UV and far UV, these efficiency curves are the previous state of the art. And the y-axis here is quantum efficiency. So that's a measure of, for every 100 photons that hit your detector, how many of it does it actually measure? And for like some contrast, for your cell phone camera and the visible, the quantum efficiency is probably like 80%. For film photography, the quantum efficiency is more like 5%. And so for this wavelength range, the best detector that you could buy 10 years ago gives you efficiencies, between 18, maybe the max is 18 over here, and like 12 over here. So you're throwing out a tremendous number of photons, and you can't even look at the bright things that have a lot of photons. So you're really like in a regime where you're only looking at faint stuff, and even that is coming through fainter because of the detector technology. So some of the work that I did in graduate school is these different lines up here. We took these detectors from this image, we applied some different optical coatings onto them to improve the efficiency. And so we were getting efficiencies above 50%. And then more work has happened since then where we can get efficiencies that are on the order of like 70% in the ultraviolet range. And the other benefit of these detectors is that you can look at bright objects. So one day I'm going to get that picture of the Orion Nebula in the ultraviolet. And working on these detectors, I sort of started the work before I really got into the science of the ultraviolet and why it was interesting. And so since then, I've developed kind of my own specific interests in the UV. And I'm really into galaxies, in case you couldn't tell from like all the pictures I showed at the beginning. But one of my big questions is like, why do galaxies look the way that they do? And how do those galaxies interact with their environments? And so this image is from a large scale program called Galaxy Zoo to just show you the like kind of weird and wonderful variety of galaxies that are out in the universe. They are, I see a question in the chat about what's the dynamic range of the new detectors. With a single frame, you can do up to about 10,000. So from like 1 to 10,000 photons in your image. The previous ones, they can do about like 1 to about 500. So this is almost like 2 orders of magnitude better for dynamic range. And then with the new detectors, you can take many images and then stack them up. And yes, this is a galaxy. This is not a comet. This galaxy is probably falling through a cluster that's like causing a bunch of its gas to come off of it. So I'm curious though about like, why do you have this huge diversity of galaxies? You have ones that are elliptical, you have your spiral galaxies, but you got a bunch of weirdos, galaxies undergoing mergers, galaxies that have no new stars in them, and then galaxies that are just like bursting with new stars. And another way to think about this, especially the galaxy environments, is, the galaxy that we look at is a very small part of this much, much bigger halo that the galaxy exists in. In this sort of artist representation, the galaxy is just this teeny little bit in the center, but it's in a halo of mostly hydrogen gas, some other materials like a little bit of oxygen, a little bit of carbon. Some of it is coming from farther out into space, pristine hydrogen from the Big Bang coming in to feed the galaxy. Some of it is coming out of the galaxy. A supernova explosion goes off and you get like a big outflow, some of which just continues onward and some of which falls back down on the galaxy. But the environment of the galaxy is a key part of being able to understand like why it looks the way it does, how it has that morphology and structure, like what else is around it. But the trick is observing this is hard because there's no stars in it. It's just hydrogen for the most part. And so we have to look with specialized telescopes, and again, mostly in the ultraviolet, because if you just have hydrogen, the primary emission line of hydrogen is at Lyman alpha, which is at 1216 angstroms, which is in the space ultraviolet. The other thing that I'm curious about and is sort of related to the galactic environment is how the universal rates of star formation change over the history of the universe. And so we actually live in a time of declining star formation, which feels like is like a tremendous bummer to me. I like really wish that wasn't the case. But like back when the universe formed at the beginning of time, the star formation rate was low. That's like over here on this plot. The star formation rate was low because like nothing had happened yet. The stars are just forming. And then very quickly we get this big peak in star formation that happened about like 3 years after the Big Bang. We sometimes refer to this as cosmic high noon, that like this was the time when there was the most stars forming in the universe. And then ever since then, in the like 10 billion years since then, the rate of star formation has been declining, and I want to know why. And we think that this is really related to the material that's around the galaxy. So the two missions I'm going to talk about today in the remaining time that I have are both focused on observing this material around galaxies, mostly via hydrogen emission, although one mission is looking at oxygen in this material, and trying to map it in taking like a two-dimensional picture of this gas. So the first one is a balloon telescope that's called Fireball, which is an acronym for the Faint Intergalactic Medium Redshifted Emission Balloon. The project is led out of Caltech, but it's a really nice team of many different institutions and lots of early career people. So when I was a postdoc at Caltech, I was the project manager and project scientist for this, and I got to learn like a lot of hands-on, mission design from doing this project. So we're looking at this interesting atmospheric window. So I showed you those transmission plots in the atmosphere, and they're all missing this window, which is that if you go high enough, about 40 kilometers into the stratosphere, there's a little gap between oxygen and ozone absorption. The higher up you go, the bigger this gap becomes. But if you have your balloon with a telescope hanging from it at about 40 kilometers, you can observe in this like narrow bandpass. So this is an angstroms, or 200 nanometers. So we're looking at particular emission lines at galaxies that are a certain distance away from us, just so that the emission lines land in this window. And the balloon telescope process is like a very interesting thing. Everyone is into balloons more recently because of the Chinese spy balloon, which was like, that was such a great day for me. It was like so fun to have balloons be like in the news. So our balloons don't get shot down out of the sky by like military jets. We launched them from Fort Sumner, New Mexico. This is a picture of me. I was cleaning the mirrors, one of the mirrors of the balloon. We have two large mirrors. There's one here, and then there's one like down here that kind of looks upward. And the design of the telescope is very strange if you think of telescopes as like the type that you use on the ground, but because this is hanging from a balloon, we had to do a bunch of different things for the optical design to be able to observe with it. So it doesn't look like a normal telescope. And then this is showing right after the launch. So the telescope is down here, this like little thing. And then there's a parachute, which is what this red part is. And then this whole thing is the balloon. When the balloon is launched, we only fill the top of it. And then as it ascends through the atmosphere, it'll expand and become like the full circle of the balloon. And ballooning is like this, now it's in the news, but it's this weird way to do science that is like not as expensive as going to space, but it gives you these different access points than the ground. So you can test out new technology, you can do pilot studies for new science, access to certain wavelengths, and it's much cheaper than going to space. But it is a little kooky. You have to wait for the weather to be good. You go to these like very remote places in order to do it. NASA does ballooning around the world. The program is called the Columbia Scientific Ballooning Facility, and it's a part of NASA. And they have like these teams of balloon people who go, they're based in Palestine, Texas, but they do the launches from New Mexico, from Sweden, from Australia, from New Zealand, and also from McMurdo Station in Antarctica. They go down during Antarctic summer and do balloon launches. So I had worked on Fireball for, like a really long time. And in 2018, we had our launch of the telescope with the detectors that I had worked on developing. And so I have some drone footage of when we had the launch. So we operate in this municipal airport in New Mexico. And we wait for the weather to be good. We also have to predict that the trajectory of the balloon once it gets to the stratosphere is going to be good. And then they decide, okay, everything weather-wise is working out. So they lay the balloon out. It takes about an hour to fill it up. Ours is about a 40 million cubic foot volume when it ascends all the way up. When it's full, they let it go. The telescope is on a crane called Big Bill. Big Bill drives around to like keep everything lined up so that when the balloon ascends and is fully vertical, the telescope can just like drift off the end of Big Bill. There won't be any like big shocks or jerks. And this was actually a very gentle launch. Like you see the crane drive away and then the telescope just lifts off. And you can also see that there's nothing around here. There's a municipal airport, which is mostly used by, there's a military, like an Air Force base that's about 40 miles away. And sometimes they come and like do landings. But otherwise, no one's at this airport. The town has about 800 people. You can like see it in the distance. You can see the shadow of the balloon. And we had some GoPros on the telescope to take video. And actually you'll notice this is early in the flight. When we ascend higher, the Earth is round, as we all knew. And you can see the balloon is much, much bigger now because the telescope is at a much higher altitude. It went up to like 130,000 feet. We have the two doors that open up. We do our night of observing, and then the telescope crash lands at the end of the night. And then we go find it and pick it up. And so there's an explosive charge that separates the balloon from the parachute, and they both float down somewhere. They land on someone's property, and NASA has to figure out who owns it. They have to get their permission to go drive onto the property. And then they build a road if they need to. And like sometimes the payloads end up in like ravines and they have to like pull them out. This was just in a field, so it was like mostly fine. And so here's a picture of the team. Some of the team, some people are sleeping when this is happening because we've been up all night getting everything ready. And the funny thing about these balloon launches is, so one of the locations that we do them is in New Mexico. And so Fort Sumner, New Mexico is here where this first dot is. This is Roswell down here. And like people started seeing aliens at Roswell in like the 1950s, and the US government started launching balloons in New Mexico in the 1950s. And the whole thing is weird. The balloon looks weird when it's in the sky. The material that crashes like can get spread places, and then you have this strange metal. In the early days of ballooning from New Mexico, there was a lot of classified experiments. They were doing like tests in the upper atmosphere, and then the experiment would land, and a bunch of government men would show up at someone's farm and be like, "Hey, we dropped something in your farm. You can't look at it, and here's a briefcase full of cash." So like, of course people thought that there were aliens. They don't give briefcases of cash anymore unless they're in South America. Now they like give a check to the person, but they still pay them because they're like, "Oh, we're sorry for messing up your farm." So this was our flight trajectory. This part is the ascent. We get up to 130,000 feet, and then the winds were really calm that day. So we like barely went anywhere. We like sort of floated around. We landed about 50 miles away. Albuquerque is here, Santa Fe is here, Tucson. It's actually like not that far off the screen over here. And this flight is so that we had to cut it down at 1 a.m., which was not part of the plan. So the flight was cut short, and this picture is a real picture. This is Fireball down here. Someone from Los Alamos took this picture, posted it on the internet. Somebody else found it and was like, "Hey, I think this is your balloon," and it is. It was an almost full moon when we launched. And the balloon here is not, this balloon is teardrop shaped, and the balloons are supposed to be spherical. And the balloon isn't because it turned out to have a hole in it when it was launched. Like back in this video of the launch, if it will play again, I can like show you the exact moment that we think something went wrong. So they fill up the balloon, and when they let the balloon, like they fill up part of it, then they let it go, and then they continue to fill it up. And there is a, let me see if we get a better view here. Okay, so like right here, there's a little barrel that is like holding the top of the balloon that's full of helium, and then the rest of the balloon is like laying on the ground. And we think that the barrel and the rest of the balloon, there was like too much tension along like the part of the balloon that was not inflated, and that somewhere around this point, there was like a tiny tear when it went up. And then as it ascends through the stratosphere, that tear gets bigger. And so what ended up happening is the balloon reached a maximum altitude, and then it just started descending, and it's supposed to stop at some point and like settle down. And it just kept going. And as you drop through different layers of the atmosphere, they're moving in different directions, and the balloon's trajectory becomes hard to predict. And we have to do a lot of work with the FAA actually, because like if we look at this trajectory, depending on how how this is moving. Like, you're on the flight path into Albuquerque, which is fine. They will divert planes around it, but like, as this drops, that becomes harder and harder to do, and the motion becomes more unpredictable. And so they cut it down at 1 a.m. because they didn't know where it was going to go. And if it starts to go over Albuquerque, like, you can't cut it down because it just lands somewhere and there's too many people there. So that was a huge disappointment that, like, we put all this work, the telescope actually worked really well, but we didn't get the height that we needed for the nighttime observations to use that balloon window. So our plan was, okay, we're going to, realign everything and then fly in September of 2020. And we were doing our, some of our alignment in February 2020 from New York City, because some of our collaborators are at Columbia. And like, here we all are, we're like so happy and we don't know what's coming for us. So obviously, like, things slowed down a lot and we restarted in late 2021. We've had some other issues, but we're working towards a 2023 flight. So I'm hoping that this September we'll be in Fort Sumner with like the refurbished telescope, an upgraded detector that we'll put in it, a few other improvements, and then and a balloon that won't have a hole in it. And hopefully we'll be able to observe that hydrogen around galaxies. And then in just the last couple of minutes, I wanted to talk about Aspera and a different way of observing the environments of galaxies. So Fireball looks at sort of distant galaxies. We're looking at like a couple billion years in the past. And Aspera is another mission which is looking at nearby galaxies and nearby galaxies that are specifically edge on. So this is a simulation. There's a galaxy in here, it's just been blocked out because it's much brighter than everything else. And this simulation is looking for oxygen emission in the halos of these galaxies. And so the brighter areas are where there's oxygen, and then the fainter areas are where there isn't. And the oxygen is this like interesting filamentary structure in the simulations. And so what we want to do is actually measure, like, is this real? Is this how the environments of galaxies really look? There's very few observations because this is at 1032 angstroms. It's a really challenging wavelength range. It's in that part of the spectrum where there's 0.03% of coverage. And there's been some limited observations that are shown down at the bottom of edge on nearby galaxies. These like little squares are where a UV telescope in the 90s looked. And in some instances it found emission, and in other instances it didn't. And so we want to do a more systematic search of some nearby galaxies. So this project is called Aspera, which is from the Latin phrase ad astra per aspera, to the stars through difficulty. So the PI is another professor at the University of Arizona, Carlos Vargas, who came to Arizona as my postdoc, and we've had such a wonderful time together. And when he first arrived, he didn't think of himself as a telescope person. He was like, oh, I like to do observations. He thought maybe about going into industry and doing something else. But he had this idea for a telescope, and we had such a great time working on it. We brought in these other people from Arizona, some of whom are shown here, and a bunch of grad students to develop a concept. We submitted it to NASA, and they were like, we submitted it in December of 2019, and they said, no, thank you. It was not selected. And so we reformulated it in 2020 during the deep pandemic for a new size of mission that NASA was requesting, where you could do small satellites up to $20 million. And we worked so hard on it, and it was selected the second time around, which I feel like is a good indicator that if someone says no, you should just keep going and try again. And a small sat is this new size of space telescope, or just satellite, that is really enabled by the miniaturization of a bunch of components and the easier access to space, where you can do ride shares. So we know HST, the size of a school bus, that's a NASA flagship mission. NASA has these other intermediate class missions. There's a medium explorer that's a couple $100 million. GALEX, the UV telescope that I had some pictures of from the beginning, is a small explorer. It's 150 million. You can have smaller ones that are 40 million. And then this new Pioneers class is a $20 million cap. And you can have even smaller ones that are this big. They're just these. So the small sats have units of 10 by 10 by 10 centimeters, and you have a 6U or a 12U. Aspera is about the size of a mini fridge, and it has 2 channels. if you like optical design, I have this slide. So the light, it's also a strange design for a telescope. It's just doing spectroscopy. So we don't take images, we'll take like long slit spectrum. The light comes in through here, bounces off an off-axis parabola as the primary mirror. There's a slit here. There's a toroidal grating, and then the detector is actually right here. And we have two channels that are looking at slightly offset parts of the sky. And so we're doing spectroscopy because we want to be able to capture a very particular emission line and be able to tell both where it is in space and its velocity and like how it's moving. So we have a sort of little simulation of how we would observe a galaxy. So we have that simulated galaxy, and then we put some noise on it. And then we start to look at it through the two long slits, and you do multiple observations over many days. You can kind of build up a two-dimensional view of the galaxy. And this is a really tiny telescope, so it actually takes 14 days to look at one galaxy. And over the course of our roughly year-long mission, we'll probably observe 10 to 12 galaxies. So it's not a lot, but it's enough to sort of figure out, like, is this the way that the galaxies look? Is this what their environment is like? Or is it some other thing? Or is there nothing there? In which case we'll have to think a lot about, like, well, what's going on? The other really cool thing about this project is that it's small enough that we are doing it all at the University of Arizona. It's not being done at like a NASA center or an aerospace company. We're like building the components in-house, and we have a bunch of graduate students that are able to like work on it and like learn hands-on mission building. So this is a model that we built of it. So there's like someone, you can see someone holding it for scale. These are the two entrance apertures here and here. And then we're practicing some optical alignment with an interferometer. So this is Carlos, our PI, testing things out. And we have our anticipated launch for this is in 2025 with 9 months of operations, 10 targets. We're like in the middle of calendar year 23. So we're working through the implementation. We're like ordering stuff, waiting for parts to come in so we can start to put them all together. And if you're interested in following the progress of the mission, we actually have a really active Instagram account that's called Aspera Telescope. We have a fantastic undergraduate who like does all the content for the account, and you can like see how things are going for us. So I guess I'll end here, and I'm happy to take any questions. And I want to thank you for coming and listening in. So there's been like a huge improvement in UV astrophysics in recent years from like these technical improvements. And we're eventually going to be in an era where the Hubble Space Telescope doesn't exist, but there's still a lot of things to discover if we have the UV telescopes that can do them. And thank you so much for inviting me. And I'm happy to take any questions.
Thank you very much. That was great. Thoroughly enjoyed it, and we learned a lot. Yeah, I'm not sure if everybody knew how much we as humans are missing, actually. Thank you very much. Letting us know all these details. And I hope you see the kudos coming your way through Zoom.
Yes.
Great. Okay, now the floor is open for questions. Let me start with the panelists. Anybody from the panel has any questions? Okay. We have one from John. He wants you to discuss a little bit about the physical absorption mechanism that affect your observations.
Yeah, so almost all of it is due to the fact that the absorption depth of UV photons in any material is typically just a few nanometers. So the UV photons they also are like very well matched to many emission lines. And so it's like easy for the UV photon to get absorbed by a molecule because it perfectly matches a particular emission line of the molecule. And then if it hits a surface, like especially like plastics or like organic materials, it'll get absorbed like right in the very top of whatever the thing is. And so it will tend to it'll tend to collect like damage of whatever the surface is. So if you have any, like in some telescopes, you use like fibers or certain lens materials, and the UV photons will be absorbed right at the front of the lens, and they'll just basically destroy the front of it. When this happens with plastics, it's called solarization. If you like leave a piece of plastic out, it like gets all opaque and crackly. Like that's what's happening. It's basically UV photons that are destroying the very top layers. There is also extinction from literally everything. Hydrogen absorbs the UV, dust absorbs the UV. It interacts really easily with basically every every molecule. So the other challenge is if you're looking at things in the galaxy, there's like dust between us and those objects, and so the UV can be extinguished because of that.
Perfect. Thank you. Chris, you have a question?
Yeah, I'm a big fan of the Carruthers telescope on Apollo 16. How would you... Well, I assume you wouldn't turn down a UV telescope on the moon, but I wonder what the advantages or disadvantages to having one parked up there, even a modest instrument. What do you think?
So, I mean, the advantage is like no atmosphere, so like that's great, and you would get like a good 2 weeks of darkness when the telescope is in the nighttime part of the moon. The disadvantages would be the data rate down, like getting the information back down to Earth. Like the farther away you are, the slower the data rate is. So you just have to have a good way to like coordinate with it, but probably there's no disadvantages if I'm being honest.
All right.
Okay, perfect. So let's go with the rest of the questions. So in building UV telescopes, so one important part would be the mirror. We know some coatings that are used for visible and infrared. The questioner says she knows that gold is used in JWST because it's a reflector in IR. And aluminum or silver for visible. What coating do you use for UV?
So we use aluminum with a magnesium fluoride overcoating. That gets you down to maybe the middle of UVC. If you want to go below that, you need a lithium fluoride overcoat on the aluminum. So they're all aluminum mirrors, but with different materials on top. And the aluminum will create an oxide at its surface, and the aluminum oxide is absorbing in the extreme UV. So we put this other coating on a fluoride, which doesn't absorb as much. The issue with the fluorides is that they're very hydrophilic. So if they're in a high humidity environment, the coating will start to degrade just from like exposure to water. So you like coat the optic and then put it in a box and fill it with nitrogen, and then when you do, you try to like limit the exposure that it gets to other things. There's been some development in kind of making better overcoats, like having the lithium fluoride be a stronger coating where it doesn't absorb as much water. And actually there's been a lot of progress in that. So the Aspera coatings, we're trying a new type of lithium fluoride process that will hopefully mean that it's easier to like do the alignment. It's easier to do the testing because you don't have to worry about the water contamination.
Okay, thank you. And let me now switch to the on the ground, in-person audience. Do they have any questions right now?
Yes, we actually have a couple of questions. You, sir? I don't know. I'll try to relay it. The question is that with all the different wavelengths that can be imaged, can any of that capability be used to image dark matter? Did I get that right?
So interestingly, there's some models of dark matter where it interacts with itself and like has a dark matter decay rate of a certain amount. And one of the potential signatures for that would be if there's like excess ultraviolet light coming from. So for example, there's these two parts of our galaxy called the Fermi bubbles that are these high energy bubbles coming out of the plane of the galaxy. So it's in like the North Galactic area and the Southern Galactic hemisphere. And they're like lobes of energy. And so there's some discussion about what's the origin of those bubbles. Is it dark matter annihilation creating this excess energy? And so if there's like a UV kind of edge to that bubble, and then we might be able to trace it back to a particular type of dark matter that would be causing that annihilation.
Okay, thank you. And before we go to another question from the audience, I have a related question from Zoom. So let me ask that. So now talking about the environment the galaxy is in, you mentioned in addition to hydrogen gas, there are some oxygen and carbon there. So the question is, we know oxygen is produced by stellar nucleosynthesis and mostly blown out by supernovae. So where does it originate from when found in intergalactic regions?
So we think that it has to originate from the galaxy or from a nearby galaxy. And then if there's you can imagine like a nice spiral galaxy, and then a big supernova goes off that like blows a hole in the side of the spiral galaxy. And then later a different supernova goes off nearby, which is pretty common. That second supernova has like sort of an open view to the halo of the galaxy. And depending on the size of the galaxy, the material that's ejected can sometimes be ejected fast enough that it achieves escape velocity of the galaxy and then like heads out. So this was probably formed a very long time ago, and it has taken a while to like fall back into a galaxy, or maybe it was blown out of the galaxy that we'd be looking at and is now like falling back in. So there's some like outflow that leaves the halo of the galaxy, and then some which is going to stay and like kind of rain down back on the galaxy. And because we don't have these observations, we don't really know which is the dominant mechanism. Is it mostly coming from outside, or is it coming from inside?
Thank you. Now let's go to have another question from the in-person audience.
Okay, sir.
Okay, if you are figuring a telescope mirror in the ultraviolet, what amounts to 1/100 of a wavelength invisible comes down to about half a wave in the far ultraviolet. How are you testing these mirrors, and what kind of configurations are you getting from them? Richie Chrétien or
I kind of wish I'd handed you the microphone. Maybe I should do that, because I don't think I can translate that one.
Okay. Okay. The question is, if you're figuring a mirror in the visible, if you figure that mirror down to, let's say, 1/100th of a wavelength, then when you get into the ultraviolet, where your wavelengths are like 112 nanometers, you're down to about a half wave there. How are you doing this, and how are you testing it for accuracy? That's question one. And what kind of configurations are you making in the telescopes? Are they simple paraboloids, or are you going Richie Chrétien or something more exotic? Thank you.
Great question. So for the surface figuring, for the ultraviolet, we never try to make a diffraction limited telescope. So just because it requires a level of like control of the surface that is too hard to achieve. And the pointing that the telescope itself can achieve, unless you have something like the Hubble Space Telescope, which has like exquisite milli-arcsecond pointing, you're getting pointing that's on the order of like a few arcseconds. So even if your mirror surface was like a perfect 1/100th of a wave in the UV, it would get blurred out by the jitter of the telescope, as it's just like trying to keep pointing at the same place. The smaller the telescope is, the like sort of less good pointing control you have. So something like Hubble part of its design was for that really exquisite pointing control. And JWST, it's the same thing, and the wavelength, of course, is different. So for the most part, for the UV, we just have it as, we have it to some, we'll make it diffraction limited in the visible. And you need a certain surface roughness to reduce scattering. You don't want a lot of scattering in the ultraviolet. So that's really the spec that we're going for, is like the surface roughness and just to reduce scattering. And then we test it. You can still test the surface in the optical. An aluminum with a mag fluoride overcoat will still be very reflective in the visible. So you can do a lot of testing at visible wavelengths, like the interferometer in one of the pictures I showed is it is a red colored interferometer. So we're doing all that in visible light. And then when we're finally aligned and set up, then we'll put it in a vacuum chamber and test it in the actual ultraviolet. And then your second question, so the telescope design, so for Fireball, it's a parabola is the primary mirror, and then we have a relatively complicated spectrograph. For Aspera, the design is pretty weird. It's what's called a Roland circle spectrograph, and so it has an off-axis parabola, which is technically the telescope, and then a one surface spectrograph, which is just the grating, and then to a detector. So that that Roland circle design is has been used in many other missions because it only uses the two surfaces. And so you have, as the fewer bounces you have, the less you lose to reflectance losses. So it's basically like the most efficient spectrograph design that you can achieve. So that's why we went with it. And fewer optics are cheaper also.
Okay, thank you very much. Was that enough for the questioner? Do they have a follow-up question?
Any follow-up question? We do have someone else with a question.
Sure. Let's have them ask.
Sir? The question is, how much turbulence is there at high altitudes for the balloon? Is it fairly stable, or is it bouncing around a lot, or exactly what's going on?
So if it stays at a single altitude, it's usually pretty stable. The balloon, our design has a guidance system. So between the telescope and the parachute and all the stuff above it, there's a pivot that you can, like, the balloon is kind of rotating around, and so you can fix that rotation with the pivot and track parts of the sky. There's also the balloon is a pendulum, so there's a bunch of pendulum modes, but those can be very well modeled. So we actually know ahead of time, like we know the length of the ladder, the basically between the top of the telescope and the bottom of the balloon. And so we can model these different pendulum modes. So there's a few pendulum modes that are like swinging modes, and then there's ones that are like wobble modes in the telescope. And our French collaborators do the guidance system. And so they have a mode where they like pre-compensate for that, those wobbles. And so we can, like, when we go up, we point at a guidance field and turn the guider on, and all the stars will be like swinging around, and then the French like click a button which turns on this pre-compensation to accommodate the pendulum modes, and then everything like freezes. And the pendulum is still happening, but the way that the telescope is designed, there's like a compensation in one of the optics, so it's like moving around to accommodate that. And it like actually works beautifully. Like by far the biggest challenge in that telescope is the alignment and the guidance system, because of the fact that like you're swinging around on a balloon. But in the flight in 2018, as the balloon is descending, it's moving through all these layers of the atmosphere. And so it was actually much more turbulent than expected, but the French system was so good that it was still able to guide on as we were like slowly falling.
Thank you very much. Now, speaking of the balloon, you did mention this, but let me ask you more explicitly. So are you the only team sending UV telescopes via balloons right now?
Yeah.
Okay. And how many have you launched? Was that the only launch you've had?
So the telescope has been launched 3 times. So there was a Fireball 1, which launched twice, once in 2006 and once in 2009. And I joined in 2008. So I like got to see the 2009 one, but I was like that was when I was like a first year grad student. And then then we like those two launches, it didn't detect anything. And that's partly because it had this old detector and a couple of other design choices that meant that the throughput was very low. And so in the time between 2009 and 2018, we like redesigned the spectrograph. So the two large optics are the same, but everything after that was different, to try and get that better throughput basically, and to make the field of view wider. So it's launched 3 times. It's like funny because it is a telescope you drop out of the sky, but it's also recyclable.
Yeah, that's the next question. You mentioned it crash landed, and then you mentioned you refurbished that. So, like, how much of it is usable?
So actually, a lot of it turned out to be usable. It was a little. Let me see if I have some pictures of this. We had to. Oh yeah, so I have another. I'm just going to share my screen again. I have another slideshow with some pictures, and so this picture here in the corner. So this is one of the large optics. This is actually the primary mirror, the parabola that's at the top. And in the crash, you see there's like a chunk missing from it. This is supposed to be like a circle. And it's not, because it came down pretty hard on one side. And so several optics were all damaged on the same side where it came down on. So we had to like take it off the mount. We sent it back to the company that manufactured it, and they actually ground down this edge just so that there wouldn't be cracks that would propagate. Interestingly, the optics are like so solid that the surface didn't change at all, even though like 10% of it is missing. The actual shape of it was like totally fine. So we ground it down, we re-illuminized it, and then we put it back together. So it was mostly things like that, where like we had little breaks that we needed to correct. Some of the larger structure, like these rods here, these are carbon fiber, and some of them had broken in the landing, so we like replaced them. And where it was like easy, we did some upgrades of things, but we haven't changed too much of it.
And am I right? I'm not seeing any cushioning, right? Is it just a box that fell down? No.
Yeah, kind of. So like here, there's these like crash pads that are basically just like corrugated cardboard stacks that we put on the bottom, like there's 4 of them. And then there's a couple up at the top we covered them in white. The French are very concerned with the aesthetics of the balloon, which I guess I appreciate, but like they covered them so that it doesn't look like cardboard on the bottom. So it's like a nice white color.
Nice.
It's great. I love working with them. They're like so funny. They're so great at what they do, but they're like, no, it has to be this way. Like we cannot have it look like this.
I see. And talking about the like, let's say, half-inflated balloon, somebody wants to know if there were no leaks, what would have been the diameter? What should have been the diameter of that balloon?
So without any leaks, the balloons are about the size of a football field. Let's see if I have it. Here we go. So there's many different sizes that are available depending on your payload. So it's about almost 500 feet across and 200 feet high. And so we were on this 39.57 million cubic foot balloon. So our telescope is pretty heavy. It's a little less than 6,000 pounds. We're like at the maximum limit. So we can get up to almost 130,000 feet. But if you have a small payload, you can do these smaller balloons. 11 million cubic feet, 4 million cubic feet, depending on what altitude you need to go to and the size. And the smaller balloons are easier to launch, like the wind, there's more tolerance for wind and stuff. So typically in the flight campaign, they'll launch like 3 or 4 of these really heavy ones. And then they'll do several more like student projects can go on these like smaller balloons.
Thank you. And then the next question is from an electronic engineer who's very interested to know if you can tell us higher level view of the how the UV detectors work.
Okay, all right. Yeah, so let me show this other figure. Okay, so the detector is made of silicon and it has a bunch of circuitry and like polysilicon on the front side. So this view is showing like a side view, like cut through of the silicon itself. So all the circuitry is on the front. You have a bunch of, you have a controller that sends signals to the silicon, and the circuits create these wells in the silicon itself. So it's like an electric field that traps electrons. And when these CCDs were first developed, the light came in from what's called the front side, like the side with all the circuitry on it. So people would just like use that. That's where the well is. But the front side circuitry actually blocks visible light because it like physically takes up space on the chip. It also blocks ultraviolet light because all of this material is absorbing in the UV. So in the 80s, somebody figured out, oh, if you flip it around and have the light go in on the back surface, like you still hit the well and you don't have to deal with any of the circuitry. So back illuminated CCDs have been used for astronomy for like a couple of decades. They actually only came to cell phones in the early 2010s. If you notice your cell phone got better at night pictures, it's because it became a back illuminated detector instead of a front illuminated detector. But so for photons coming in from the back, a visible wavelength photon travels through the silicon and then forms an electron somewhere in the bulk of the silicon. The absorption depth of the electron is pretty deep. And so the photon will be formed here and then fall down into the well, and then you read it out as usual. For the ultraviolet, the photons are formed right in the first couple of nanometers, and the back surface has this these like backside potential wells, which basically trap the charge that is created, and then you never get it into the pixel. So the process for the making them UV optimized is basically to engineer this surface so that you don't have a well here. And then, so I have like this, let's see, this process is called delta doping. You basically there's a machine that can perfectly match the silicon crystal of the detector. And so you put a single atomic layer of boron, and then you grow more silicon on, and the boron creates this electric field at the back surface where you previously had a well. Now you have this spike, your electron gets formed on the other side of the spike from the surface and then flows down into the actual pixel, and then you can read it out. And the readout process for a CCD, this figure isn't exactly a good match to it, but the pixels create this grid on the CCD, on the detector. And so your electrons will land, your photons land in one of the grid cells, they create an electron and the electron waits. And then when you're done with the exposure, you actually read it out like a bucket brigade, where you like will shift a row down, and then you have a readout register which shifts the pixels over. And at the end of the readout register, you have like a measurement electronics that says, oh, there's 8 electrons in this pixel. Then it reads the next one. It says there's 10 electrons here. There's 100 electrons, and you like read out a line, and then you shift another line down, and then you read out the line. And so it's this like sort of iterative process. So they're called CCDs, which is charge coupled device, because you can like shift the charge from one section to another in actually an almost perfect transition. Like there's very few losses in the readout process, even though you're doing like a million shifts. It's like a really brilliant system. They want to know, the guys that invented this like won a Nobel Prize a couple of years ago for it. But this is the difference between this, which is mostly used for scientific applications. This readout time can be time consuming. The device in your cell phone, instead of having a single readout point where you have to like shift all the pixels down, for your cell phone, every pixel has a readout point. And so you can like read out the image way faster because you have If you have like a gigapixel, you have a gigapixel of readout points. From the image processing side, that will make each of those readout points has a slightly different noise signature. And so that makes the processing harder. So for astronomy, we use this design where there's just one readout point, because then you can characterize its noise very well. And so the whole image has like the same noise characteristics, but you pay for it a little bit in time. And that's a CCD. I love them. They're the best.
Excellent. Thank you very much. That was a great explanation. Okay, now let's switch to the people in person, see if there are any questions.
Okay, sir? Yes. The question is whether you actually, sir, I think I'm going to have you restate it directly into the microphone, because I'm not sure I quite figured it out.
Okay, and Erica, you're still sharing your whole screen, just so that you know.
Oh, thank you.
My question is, did you guys do any research on explosions of hydrogen balloons versus helium? Helium doesn't blow, obviously, but when I saw the Hindenburg blow up, it was a large expanding ball of fire. It wasn't really a violent explosion. Did you guys ever consider using hydrogen because of cost and because of the increased efficiency of lift?
Yeah, so I mean, there's also a helium shortage. Helium is a non-renewable resource, and apparently, well, everything seems to come from Ukraine, but like there's been a recent issue in the last year because of the war in Ukraine that like there is a bunch of helium coming from Ukraine, and now it's not. And so the NASA people are like, oh, we can only do so many balloon launches because we only have so much helium. There is a company in Tucson that's called Worldview that has been experimenting with different balloon types, including a hydrogen balloon. But they were doing okay. And then a couple of years ago, they had like a not exactly Hindenburg size accident, but it was like definitely like hydrogen explosion that was enough to make people like wary of using it. And for us, the issue is more that like we basically take the ride that NASA gives us. Like NASA sets up the balloon program and like runs it, and so if we were like, hey NASA, we want a hydrogen balloon, they would be like, no. And that's actually the main thing, because like our funding, we get funded to build the telescope, but we don't have to pay for the launch. And so if instead we were like, we're going to go with Worldview and use their balloons, we'd have to pay for it out of the like main grant, and that's also really expensive. And I guess the last thing is like a lot of the people experimenting with other balloons, the balloons aren't big enough and they don't go high enough for what we want to do.
Thank you. Are there any other questions from the in-person audience?
Any other questions at this point? I think not.
Okay, so we have another question from Zoom. Again, back to the intergalactic environment. Aren't the Fermi bubbles also supposedly potential central black hole fossils from ancient galactic jets?
Yeah, so that's one of the possibilities. The kind of connection with like the ultraviolet is that if they're ancient galactic jets, they like carved out a bubble, but then they should be like, that should be it. There should just be a bubble without like activity at the edge. And the connection with like dark matter annihilation would be if we see activity at the edge that doesn't make sense given the age of the bubble, like that activity has to come from somewhere else. And the link with the bubble is more that there's not a lot of other stuff there. It's like kind of been a cleared out area. So if you're looking in like the galactic plane, it's too complicated. There's too many other things happening. Whereas like the edges of these Fermi bubbles are very high galactic latitudes. There shouldn't be molecular clouds. There shouldn't be lots of stars. There shouldn't be anything. And so then it's just like a slightly easier environment. So it's not that, I guess I may have misspoke about like the origin of the bubble, but the bubble is a really interesting place because it's this like unique environment.
Perfect. Thank you very much. And this covers it all for us tonight. Again, Dr. Hamden, thank you very much for a wonderful, fascinating talk and then answering all our questions in as detail as you could. That was wonderful. And
Thank you so
we
much
hope
for
to,
having me.
yeah, we hope we could have you back in the future to update us about your research. Thank you. So let me remind everybody that our events are ongoing in the future. Please check the calendar on our website for all our upcoming events at ocastronomers.org. With this, I would like to thank everybody, both in person and online, for joining us. And we all wish you great times ahead. Bye-bye, everybody.
Thank you. You guys had the best question.